Okay, hello there. So, what I wanted to talk about is the guy who I drew this picture of. This is my favorite physicist. His name is Tim Maudlin. Um, I'm not a physicist. I got my undergrad and only my undergrad in mechanical engineering. So I took some physics classes, um, but nothing crazy, physics at a maybe 200 level. There's some engineering classes like dynamics that end up being sort of physicsy, but whatever. I'm not a physicist at all. Um, just a fan of serious physicists, I guess. It's just cool, like asking like kind of deep questions about like what is really there, what what's really like irrefutably making up a reality. A lot of times that gets into like what's fundamental particles, fundamental theories of like what there is, you know, a lot of like, I don't want to say popular physics, but a lot of like what you'll hear physicists talk about is like waves being more fundamental than particles, that particles are just like perturbations in waves or something. Um, I don't agree with that. And a lot of that is just because Tim Maudlin doesn't agree with it. And I think he's smart. But one thing that Maudlin has talked, I've heard him talk about quite a lot, is this question of motivation. And um, he doesn't, I don't know. We have this sort of like colloquial uh, understanding of motivation, like an actor carrying out a scene in a play or a movie, like what's my motivation? What's motivating me to act, right? Um, a lot of like grind set, uh, what would you call that? Motivational speakers, people that are like trying to get you to whatever, be your best self, self help, right? They talk about motivation, like what's your motivation to quit smoking or get in shape or whatever. Like motivation is this like personal, powerful force or whatever. The way I've heard Maudlin talk about this is not in this way at all. Like, well, not at all. Like, there's some overlap, but he talks about it a lot in a historical sense. Especially when he's talking about theories of physics. What motivates one to propose a specific axiom or a specific model or to make a specific claim about the nature of reality or to uh, come up with a formal way of describing reality in a certain way or not. Um, and this has really like piqued my interest. I think it's a good way, not just for physics, right? I mean, physics is, I don't know if it's important or not. Obviously, like, there's a kind of like pursuit of the reality of the physical world that led to, real innovation in engineering, like go watch Oppenheimer. The realization that there's like more energy contained in these strong nuclear forces and whatever. um, led enterprising physicists and engineers to say, well, maybe we could make a big weapon out of uh, that takes advantage of this force or whatever. So I'm not trying to say that like an understanding of physics doesn't matter, but I was born in 1990, and a lot of what was talked about in sort of popular media about physics was talking about these weird ideas like the multiverse, string theory, and what those things claimed, right? That like measurement events were not just affecting like particles and the things being observed, but they were having sort of like global implications that like universes were bubbling off or splitting or whatever, um, based on events that were happening at this sort of quantum level. Or string theory, that like the fundamental things are these little really teeny tiny strings that like vibrate, and their different configurations lead to, uh, as they aggregate, both particles and like you know, fields or particles that eventually like create gravity and all this kind of stuff. So whatever, I was kind of like, again, never a physicist, not a physicist now, obviously wasn't a physicist when I was like a 12-year-old watching the History Channel or Discovery or whatever, listening to people like Brian Greene or Michio Kaku talk about these weird theories. And they are weird. They're bizarre, and I don't think they're properly motivated. But anyway, Tim Maudlin has been pretty influential on me about talking about the motivation of different parts of physics. And again, I hope it has some kind of like bridge outside of physics, because again, it's not that I don't care about physics. Physics has its place, but it's not the reality we live in, and especially in the modern era, is not governed by understandings of the frontier of physics, right? Physics had its place in developing the bomb. Physics had its place in like space exploration and everything that came out of that, whether you want to say that's like a big deal or like, you know, kind of wasting our time on these moonshot projects that, you know, we got Tang out of it, and we got foil blankets, but we got like, you know, microelectronics, you could maybe say, are like, you know, partly developed through the funding put into space exploration. But okay, space exploration itself, space travel itself, it's not something that impacts like your average Joe, right? It's something that is of interest to three-letter agencies that are launching satellites, and commercial telecommunications that are making telecom satellites, and that's pretty much it. Even people going to the moon, right? Like we only did that a few times, and then the question of motivation. Why are we doing this? We already beat the Russians. We've demonstrated that we have, you know, as the United, you know, speaking as an American, like we've demonstrated space race supremacy. So are we going to just keep going to the moon? How often? Every 5 years? Every 10 years for fun? No. At a certain point, you just go, okay, yeah, we went like 5 times. It's fine. We can stop now. Um, so I want, yeah, I believe that this like demonstration of this idea of motivation in physics has implications outside of physics, and that's what's interesting to me about it. So this is all from Tim Maudlin, right? I'm just parroting what I've heard him say, but he gives the example of, so there's going to be three models of time: the Newtonian, the the Einsteinian or relativistic, and then the Maudlinian, right? So we're going to go through these. So Newton. Newton had a model of time. He had to, right? He had to say something about time because time is pretty fundamental to his model of physics. Newtonian physics is probably what most of us think about when we think about sort of the reality of the world. And it's what you get at a high school and undergrad level, where you have some quantity y, and you have your axis x, which a lot of time you can call t for time. So as time is ticking along at 1 second per second, 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds. You know, if you're in a car, let's say you're in a very fast car like a Mustang or something, and this y we're going to call your speed. So this is, actually, let's call y your distance from some starting point. And what's going to happen is you start here at 0. The clock starts at 0 as well. So clock starts here, starts ticking at 1 second per second. You're starting here at rest. And what you do once the clock starts is you hit the gas. So where you're going to be at 1 second is you're going to be this far. And at 2 seconds, you're going to be further. And at 3 seconds, you're going to be further. And at 4 seconds, you're going to start to plateau. And you're going to be approaching your maximum speed here. So you have something like this that represents, no, this would be not your distance because your distance would keep going and going. Let's say this is your speed. This is your speed. Come on. Because that's what happens in your car, right? You hit the gas, you're going 0 miles per hour, you're at rest. You hit the gas, you start to speed up, speeding, and then at about 4 seconds, you feel the car start to kind of plateau. You're not getting any faster, even though you're putting the gas down, and this is going to be something like your max speed, 150 miles per hour. I don't know, this might be a little off, but it's something kind of like this, right? So Newtonian physics is all about this kind of stuff. The relationship between speed, acceleration, jerk, right? And defined with, defined a lot of times like on XY graphs like this. Newton also is a pioneer of calculus. So taking the area under this curve and realizing that that area represents, if you sum it all up, that this is equal to distance, and that these relationships exist between like distance traveled, right? That after 6 seconds, you've traveled kind of an enormous distance, and the higher your speed is traveling for a longer amount of time, the more distance you travel. Obviously, that's like very intuitive, but this mathematical formalism represents that. So Newton had to say something about time. What is time? So time, according to Newton, ticks along at 1 second per second, and he had a model of universal simultaneity, which is, again, it's very intuitive. It makes sense. When I snap my fingers here in East Idaho, there is a moment of time, and I could ask the question of when I snapped my fingers, what was going on in Lisbon, Portugal, at that exact moment. It seems like you should be able to say, well, there was something going on at that exact moment. And you could say, it doesn't matter that we're separated by thousands of miles, that something happened there at that moment. You know, this is North America, Europe, Africa, Middle East. Russia's around here in the back. But when I am here and I snap my fingers at t equals 1, that there is a t equals 1 moment everywhere. There's a t equals moment here in Europe, here in Africa. There's a t equals 1 moment at the moon. And even further away, there is a t equals 1 moment at Alpha Centauri, which is like light years and light year, or, more than a light year away. And it doesn't matter how far. There's just that moment everywhere in the universe. So that's how Newton thought about time. What that means is there can be what's called a foliation of time, and that represents at this moment in time the whole universe can be sort of like paused, and we can say what's going on everywhere. And that if we paused time at that moment and we were able to travel as slow or as fast as we want because time is paused, we would be able to like travel along and see, oh, that's what's going on across the globe, on the moon, among all the stars everywhere in the universe. And that, if you were an observer, you were able to pause time like that, you'd be able to see what was going on anywhere. Or you'd be able to ask the question, what's going on anywhere? Even if you'll never get that answer, because light itself, the medium you have for knowing anything about what's going on in the universe, is traveling at a certain speed. You can't actually stop time. You have to wait for light from distant places to get to you. All of that in the Newtonian model's it's not like a problem, right? The fact that like light travels at a speed, you could say that people in Newton's time and definitely before thought that light was a kind of instantaneous phenomenon, that like if you saw a supernova, there wouldn't be a concept of light years away. It would just, people would believe that like light is like an immediate medium, that it's transporting events as they happen across arbitrary distance. It doesn't have to travel, it's just showing you what's happening. Some people thought that, but you can retain a Newtonian idea of like there's a foliation of time that extends throughout the universe and still accept the concept that light travels, and it travels at a speed or whatever. So Einstein challenges that idea by saying, actually, there's a speed limit to light, and that has implications about, not that just the speed of light itself has implications about space or about time, but he proposed a model of time and space itself that's sort of coupled, right? Where you've probably seen these diagrams where you have a massive object somewhere in a space, and what's called space-time sort of bends around massive objects. This has been sort of like, this model has been sort of confirmed that, when you have a really massive object, that you affect space, but that can be measured with measurements of time. So like if I send a satellite near a really massive planet or near a star or whatever, the proper time that a clock that's like on a spacecraft or whatever traveling near that thing or traveling fast or whatever, that it clicks along slower. And you can observe this with like precise clocks, you can do all kinds of experiments, and you don't even have to send things out into space. You can just like move things around inside of a lab, and you can measure the amount of like what's called time dilation. So this idea of Einstein's, that you don't just have space and time as totally separate things, but you have a model of space time. There's like one fabric or whatever of the universe that is space and time together. And they're sort of affected by the measurement of space and time is affected by who's making the observation, right? Because if I have here on Earth, I send a spaceship in one direction and a spaceship in the other direction, and this guy's going to go pretty slow. He's going to go 500 miles per hour on his trip, and this guy's going to go 150,000 miles per hour on his trip, and they're going to go, for the same amount of time as they measure it. So they're going to have a clock that says, go this direction for 30 seconds. And, well, let's say more like 30 years, right? Then the difference will be more pronounced. And then turn around and come back, and so the 10-year-old astronaut that you have will be 70 years old by the time you come back. People on Earth will be clocking like 70 years, and they'll be like, okay, they're supposed to go out for 30 years and come back. This ship is going to come back, and it's going to have, that 10-year-old astronaut. Each one has a 10-year-old astronaut. And the people on Earth will observe that 10-year-old astronaut on, here's ship A, here's ship B. Ship B is just going to go out for, about 30 years and come back in 30 years, and the 10-year-old's going to be 70 years old. And all of the 10-year-olds, when the ship left, will also be 70 years old, and they'll see that happen. This ship, and it's not the right amount, like, it would probably have to be going much faster than 150,000 miles per hour. It would be going like a bajillion miles per hour average on its trip. But that one that went out super, super fast for 30 years and came back for 30 years, all the people on Earth that saw that ship leave are going to be dead, right? It's going to be a lot longer than 70 years that passes on Earth by the time that ship comes back. But the 10-year-old on that ship will be 70 years old, or it will be, as measured by his own clock, his own watch that he took with him. So both people on both of these ships experience a 60-year journey, 30 years out and 30 years in. But because one was going like much, much faster, like close to the speed of light, right? Let's just say like, whatever. I picked a bad number here, but let's just say these people are going like 99.9% the speed of light. That's how fast they're moving on average through the trip. Then same thing. They'll be like, holy cow, 30 years, let's turn around, 30 years back. And that's what these people in ship B will experience too. But ship B will come back and they'll see a bunch of other people and they'll be like, yeah, about 70 years you were gone. They'll be like, yep, we were gone 70 years. And ship A will come back and they'll be like, well, 70 years, we were gone 70 years. And the people on Earth will be like, who are you? Oh, are you that ship that left like, whatever, hundreds of years ago or whatever? So there's this thing that happens. So that can happen with speed. It can happen with, Interstellar shows this, right? That like, if you get next to really massive objects, the closer and closer you get to massive objects, like supermassive, much more massive than the kind of space you're existing in or the planet you came from or whatever, that the mass of these objects can also dilate time in the way that moving quickly through time does. And so that's what Einstein discovered, or proposed, and then subsequently there have been many, many uh, validations of of Einstein's idea that this happens, right? Doing experiments with satellites and then just having more and more precise clocks being able to measure this effective speed of relative speeds. But what this sort of not implies, it just proves that you can have the experience of being an observer in one of these frames, right? You can be an observer on Earth, you can be an observer in ship A, you can be an observer in ship B, and you experience something, you see things happening around you, and you experience your own sort of um, local reality. And it's not like it's not true. You watch it and it's ticking along at 1 second per second. But according to another observer, they have a different story of what happened there, right? Observer A sees ship B and the observers on Earth as progressing through time like on fast forward. They're aging much more rapidly, their clocks are ticking super fast. And the observers on Earth and in ship B looking at ship A see it like boo, like going super, super slowly through time. That time is like dilating for them. And both of those things are true at the same time, right? That it is just a fact about the fabric of space time, about how we move through the universe at speeds and at levels of gravity, that those things are both true. They're not incompatible. And so part of this like observer effect, or this like framework of time and space, led Einstein to say that Newton's idea of simultaneity was invalid, and that actually the formalism that Einstein developed did not need a foliation of space-time. It didn't need, and it couldn't really have, in the same way that Newton thought about it, it couldn't have a simultaneity, right? Because if I snap my fingers, sure, there's that moment for me. I hear the sound, and I can imagine that that moment exists on Alpha Centauri and on the moon and across the hall. But what Einstein says is really, it depends who's observing that event, that instant. Because if I'm observing it right here, yes, it's instantaneous. But depending on like things moving around me or at great distances from me or at different, like when that event happens in a sequence of other events, can actually be can be seen differently. Like something that to me is like a past and a future event can be seen opposite by someone in a different frame of reference, right? They're not necessarily going to see, you know, it goes beyond just like something happening like faster or slower. You can imagine that like things moving in opposite directions at very, very high speeds, and especially when you bring in like a third party, like some event that they're watching that has relative motion compared to like those two observers, they might say and they might report that something happened first and then something happened later. But depending on where it is in space and how fast it's moving and in what direction, the other party might actually say, no, actually, event A happened before event B. You said B happened before A, but we actually saw A happen before B. So um, Newton said, or sorry, Einstein said, we're just going to get rid, there is no preferred foliation, right? There's not like an event, a moment where you can say something happened in the whole universe. Like there's just, it depends, it's relative. It's relative from your point of observation, right? So we've gone along with that for a very long time. Most people believe that about physics and the reality of physics. What Tim Maudlin has suggested is that there is a foliation of time, that Einstein jettisoned a preferred foliation of time, and that we actually need to bring it back. We have to have a preferred foliation of time to explain new phenomena. So those phenomena are experiments that have been done that have proven correlations at what's called space-like separation or light-like separation, space-like separation, right? So let's say you have a little machine here, and it takes an atom that has, let's say, 3 electrons zipping around it, and it splits up those electrons, and it sends 1 electron over here, and it sends 1 electron over here at the speed of light, and it sends 1 of the electrons over here really, really fast. And it doesn't matter how far apart these are, depending on how fast you can do an experiment, but let's say it sends it 100 miles and 100 miles in this direction and 100 miles in this direction. And so there's a certain speed, if we want to talk about point A, point B, and point C, there's a certain speed that light that you would have to travel to get from this point to this point, and from this point to this point, and this point to this point. And there's a certain speed that light travels at. And how they set up these experiments is they say, before light can travel from point C to point B, or from point A to point B, or from point C to point A, or A to C, or vice versa, before that can happen, what I need you to do is I need you to conduct a really fast experiment on this particle. And I need you to do it here, and I need you to do it here. So once you get, like, right, these particles, these electrons are released at the same time to 3 locations. And the way you set up the experiment is you say, once you get that electron, like once it shows up, make a measurement on it really quickly. And so that happens. And it happens so fast that it's faster than light could travel at the moment the experiment is conducted. It's faster than light could travel from any of these points to each other, right? So what that means is the outcome of the experiment could not be, it's impossible for it to be influenced from light traveling from one location of experiment to another. So these things are happening locally. They're happening before there could be a physical influence that we know about from one of the experimental points to another. And what they find when they conduct these experiments, these electrons that are stripped off the same atom, like, this is stupid, right? I don't know exactly how these particles are prepared, but they're in a state that's called entangled, where what happens to one particle has a correlation to what's measured on one particle is correlated to what's measured on the other particle always, right? If the experiment succeeds at all 3 places, what you'll find is that if the particle that landed at B is pointing up, the particle that landed at A is pointing down. And the reason they do these experiments in 3s is if 2 of them are up, the other one has to be down. Or if 2 of them are up, the other one has to be up, or whatever. You know, there's like some kind of combination of states that you never see coexisting, right? You're never going to see one being like left, up, and left, or whatever. You know, like it always has to be like left, up, and up, or whatever. You know, and this just has to do with like when you make an observation, it's just like where the electron hits on a screen after it passes through this like weirdly shaped magnet. So, but what they find, and models of quantum physics predict this, and it's strange, and it's actually observed in these experiments, is that these particles, the way they're measured, it has to have an influence, right? What is measured at point A is actually affecting what is measured at points B and C, and like vice versa among them, kind of. So like there's certain correlations about these are real experiments that have conducted, that have been proven, right? Doing these experiments where you measure something at a moment so quickly that there's no possibility for light to travel from one point to the other. There's no way of communicating at light speed from one place to the other. What you find is that what is measured in one place determines what is measured at the other two places, or what's measured in two places determines what's measured at the other place. And so what this means is that there has to be this kind of inequality that the event of measuring something at one point is actually affecting the outcome across this vast distance at another place. So what's been proven is that if I have an entangled pair of particles, if I alter the spin to one, I will create the opposite spin in its twin elsewhere in the universe, no matter how far away that is. It could be from here to Alpha Centauri. Like, once something's measured in this place, it cannot be measured elsewise elsewhere. And what these like tri-particle experiments show is that there is a causation, right? That there has to be a causation from the sort of forcing of a particle into a state at one location to its like the paired particle elsewhere faster than light. And so this is just a fact. Like, it is called Bell's inequality. Bell's inequality has been proven by these experiments. So now Tim Maudlin, coming back to the question of foliations of time, has said Newton had very good reason to say we don't need foliations of time, right? He was rightly motivated to remove a preferred foliation from the model of space-time, of a preferred foliation from the model of the universe, of physics. And what Maudlin is saying is that Maudlin is motivated to bring it back. To say, in order to say how these particle measurements are affecting the outcome of particle measurements done elsewhere in the universe at space-like separation, we have to bring back an idea of a preferred foliation, like an instant of time in the whole universe. Because if what's measured on B affects A, or what's measured on A affects B, we have to be able to like reason about, well, which one was causative, right? Like, did the change on B create the measurement in A, or did the change on A create the measurement in B, right? In order to have this, because it happens at superluminal speed, like it happens faster than light, Maudlin's saying we got to bring back the preferred foliation. Like, and what the reason, like, I think this is an interesting example of motivation is these are the terms that Maudlin puts this in. He said Einstein did not know about Bell's inequality. Bell proposed inequality after the death of Einstein, and that Einstein would not have been motivated with the information he had and his process of reasoning at the time of his work, in the time of his life. He had nothing that motivated him to ask the questions that John Bell was asking when he came up with this idea of Bell's inequality. So Maudlin says, I don't expect Einstein to have, basically he's saying, like, if I were in Einstein's shoes, I would have also removed the foliation, because I would have seen that, like, the way the foliation was proposed in Newton's mechanics was not valid anymore. It was like, in the new model, it wasn't needed, and it sort of interfered with a clear understanding of what was happening in reality. He's like, but Newton didn't know about these inequalities in the theory, and he certainly didn't know about the experiments that proved that they actually happened, that these things at large distances, faster than light could travel, that there was causation at these speeds. And what Maudlin says is, I am motivated because I have absorbed this new material. I need a foliation again in order to make, not whatever. He's not saying, like, definitively this is the, like, full reality of the physical world, but just he's motivated to bring the foliation back. And that he doesn't say Einstein was wrong. He says he was properly motivated with the information he had at the time to remove it. I am now motivated by the information that I have to bring it back. And I think this is a fascinating idea. And I think it's something that, like, absolutely has implications for all kinds of elements of social thinking, of politics, of whatever. To always be asking the question, what is the motivation behind any particular course of action, behind a certain way of viewing the world, of theorizing about reality, about understanding where we are in the world. Like, what motivates us? Like, right? And I think I see this all the time in software engineering, right? Some engineers, I think, would realize that a lot of what they believe and what they propose about, I don't know, like, ideal ways of writing software, of setting up software architectures, that it's just not properly motivated, right? I had an engineer who I worked with kind of recently who, on his first day in our company, said, you know, I would really like to see the software service that we provide being served as a set of functions on serverless cloud utilities. He wanted to change our app to become a serverless application. What was motivating that? Well, he didn't know anything about the application. He didn't even have access to, like, our company's repos or anything at the time. So he was motivated, I mean, in my opinion, by an ideological commitment to providing serverless software. I think he was probably motivated by the marketing material that proposed the benefits of serverless software, because he didn't know anything about a particular software product. He didn't know what it cost. He didn't know what the latency of API calls to our product was or anything like that. He just said, I'm going to transform the products wherever I land, whatever company hires me. I'm going to make it my mission to take their architecture and make it a serverless architecture. So that was something he was very excited about. But what was the motivation? Didn't have anything to do with customers at our company. Didn't have anything to do with problems that we had in our product. Didn't have anything to do with any of that. It was just, he was just like intrinsically motivated to transform all software in the world to serverless software, which is, I mean, it's pretty stupid motivation. I think it's unmotivated, basically. I don't think it has a valid motivation. So, yeah, I think, and I mean, again, I think this idea, this concept of motivation, what is leading you? What's like the sort of valid set of reasons that you have for doing what you do, for believing what you believe, for getting up and doing whatever you do every day, you know? I think this idea of motivation is like really critical, and we got to be introspecting on this and being like critical of ourselves all the time about what's motivating me to do XYZ. Because I think a lot of times you'll find that what's motivating you is really flimsy. It's like, I want to be viewed positively by somebody in, not even in my life, right? I want to create a certain sort of like aesthetic to my life that's viewed through like social media platforms by other people, and is like, I want to create an appearance of my life that's like envious to other people or whatever, right? I think this is a lot of what we can end up being motivated by. And I just think when you really pin it down of like what's motivating you, you can see quickly, maybe not that you have like a rock solid bulletproof motivation for doing everything that you do, but I think it's really easy to see when you have a shitty one, and to realize that like you're acting out of a kind of reflexive or stupid, or that you've just like gotten caught up in kind of a hype cycle or whatever, you know, that you've started to believe marketing material or somebody else's opinion that you haven't really considered. It just seems to be sort of like accepted by everyone around you, or people you think are smart or whatever. And that's just not good enough, you know? God blessed us with brains, and by golly, we should use them to good effect. And one of the things we should use them for is to think about our own motivations and to come up with better ones when we have shitty ones. So that's it. Bye bye.